Okay, so let's get started. The number of students is decreasing, as I was saying earlier. That's okay. So not much logistical announcements except for there is a assignment due next week. It is somewhat challenging, in the sense that it's the first time you're working with text data, unlike torch vision stuff that you did with assignment 2. So so try to start early. I know I've spoken to a couple of teams, a couple of groups, but I think if you can start early, then for second question of assignment 3, then you can try to use your own, maybe some interesting language that you like. Okay, and in particular, going from English to that language may be a little bit easier, but starting from that language to English will be a little bit messy. Because you cannot use word2vec slash glow or something. I think it mentions try to use it for going from English to another language, but for other languages you don't have the same. At least you don't have word2vec slash glow. You have other embeddings. You don't have to use them. But anyway, these are all considerations to when you think about assignment 2. Question 2 in assignment 3. But it's due next week. So we are here. We have about 5. Actually, we only have 4 more lectures before we get to the end of the class. In fact, the assignment 3 that you're working on is actually one of the, I guess this one, assignment 2 and 3 are the hardest ones. Assignment 1 and 4 are supposed to be like 50% effort. I mean 50% in terms of complexity or difficulty compared to 2 and 3. So 2 you already crossed the hurdle. 3 hopefully you'll cross that next by next week. So just know that it's not going to become difficult. It's going to be easier next time. And the reason for that is, of course, that there is a project submission within a week after that, and it's a big percentage of your grade. And as I always say, this is an elective course. You wanted to learn this material, so pick a project that you can use for learning something, as well as demonstrating to other people that, hey, you know something about deep learning, and maybe your domain, right? So okay, so let's actually get back to what we're talking about. So we are going to continue talking about variational autoencoders, and also I'll recap a little bit, and you'll see that it's going to be a little bit heavy again on some amount of math. I don't think we saw much of equations over the past first half of the first few lectures, but at least the first half an hour or so there'll be a little bit of equations involved. That's just to give you a flavor of this class of machine learning, this whole sub area of machine learning. I'll mention it when we get there, but which are called probabilistic graphical models. And then there's this procedures like EM. I think EM you might have heard when you were looking at when you're looking at Gaussian mixture models, for example. There's something called EM, expectation maximization algorithm, things like that. So anyway, my point is there's this whole sub area of machine learning which is about generative models, within which variational autoencoder that we'll see is also a member of. Okay, so generative models, as you know, is basically modeling the joint distribution between input and output rather than the conditional probability of output given input. Okay, so anyway, so we'll continue there, and today's objective is to really get to generative adversarial networks. Okay, and we'll of course look at the most simplest explanations for both of them. So there are a lot of variations, and I think to get to, I think last time we saw this, right? This person does not exist, right? So to get here, so I thought there was a link at the bottom, but okay. So this is produced by a model called StyleGAN2. Actually, it does say it here. But we'll not look at these. So there's a link to GANs, and there's a link to the actual model used. We'll not look at the nuances of StyleGAN2. I mean, you can certainly use this. For example, if somebody wants to pivot in the project scope to work with GANs, you can start working with StyleGAN2 if you want. But we're only looking at the basic GAN model, okay, today. So in fact, let me just recap the goals. So goal is we're gonna try to finish up the treatment of variational autoencoder. Last time we briefly, kind of spent a lot of time on autoencoders, and then we briefly touched upon variational autoencoders. I'm just going to again differentiate what is the difference between them, and then we kind of finish the treatment, which involves, hey, what is the objective function that you are trying to minimize or maximize, and how do they work? Okay, how do they perform in the applications? Okay, and then today's objective is this generative adversarial networks. And so we want to understand the intuition. So what changes with these models, actually last lecture and this lecture, is the objective function. So far it's been, although we've been looking at sequence models and supervised learning, the objective function has been mostly like sum of cross entropy terms or something like that. Okay, so the loss criteria has always been mostly cross entropy. Okay, whether you've been generating sequence of text like in assignment 3 or in assignment 2 where you're doing just classification, right? But here it's unsupervised learning, and so it will have its own objective function. Typically, it's a maximized likelihood type of an objective function. But you'll see that that's exactly what we do for variational encoder, maximized likelihood, but we cannot do that directly. So we'll try to do some proxy for that. And the second, for GANs, the objective function is slightly different. Okay, there's going to be difference only because they're not supervised learning problems. For supervised learning problems, typically objective function is misclassification loss or cross entropy loss or things like that, right? So it's not the case here. But really, we want to finish up this treatment of unsupervised, these two examples of unsupervised deep learning problems. Okay, and towards the end, we'll try to just differentiate between those two. Okay, between GANs and VAEs. Note that we'll mostly be talking about GANs and VAEs in the context of image data, but they don't have to be image specific. Okay, I know some teams try to use GANs for text generation. Okay, you already have like language models for text generation. Like you have pre-trained Distilbert, or sorry, not Distilbert, but pre-trained models from, let's say, Transformers package to do language generation, or other examples. But you can potentially use GANs for text related, fake text versus real text and so on. But I am not very aware of that direction. But for example, VAEs, in fact, I have some work that I'm currently working on, which is related to graph VAEs. Okay, so you can, just like images and text, graph objects, or graph is a type of data, I guess, representation. It can have its own processing. Okay, so there are models called graph convolutional networks and graph various autoencoders, which work on graph inputs and try to produce graph outputs. Okay, so just trying to say that although today's last time treatment and today's treatment is mostly about images, doesn't have to be images, it can be text or other things like graphs. But anyway, the goal is to really understand what's a VAE and what's a GAN. Okay, that's pretty much the goal. VAE has an implementation in PyTorch, but we'll see it maybe afterwards. So let's actually get back to the deck. Any questions about the overall context? These are not the only two unsupervised learning problems, and there are many other variations of problems in deep learning area. There's something called self-supervised learning, and there's also a more traditional idea called semi-supervised learning, and there are many different variations. But within unsupervised learning that most of us are familiar with, like dimensional reduction or clustering, these are two examples that you'll see from the deep learning side. Go on slide. Yeah, so I'll just briefly recap autoencoders. Very quickly recap autoencoders, but the slide deck, we are not going to cover unsupervised learning landscape. We did that last time. So really, we want to understand autoencoders and variational autoencoders for now, and then maybe in the second part we'll talk about GANs. Okay. So for autoencoders or variational autoencoders, as well as for GANs, we need a basic object. Okay, that object is basically going from a vector to an image. Okay, so it's just think of a Lego, not Lego, but some building block. And that block has to take a vector as an input and produce an image as an output. Okay, you may say, hey, how can we go from just a vector, which is a bunch of, let's say, 10 numbers, to a bunch of numbers, which is like 64 plus 3 here? or 100 numbers to 64 cross 64 cross 3? And the answer is there has to be information retained in the decoder. Okay, there has to be some information plus that initial information together can create a rich output. Okay, and so this object is basically a deconvolutional or DC or sorry, transpose convolutional network. Okay, and it's exactly the opposite of a CNN. So if you go from right to left, it looks like, hey, I passed an image and I got an image embedding. And here we're just going the opposite way. We're going from an embedding to a kind of an image. Okay, here, in fact, we're getting an image here. So and we last time we discussed briefly that, hey, this is possible because clearly, each one of these, although we're going from tensor to tensor, if you think of going from tensor to tensor as like each slice of the output tensor as like an output of a filter is nothing but a linear transformation. Each filter is literally just element-wise multiplication and addition, and that's what a linear transformation essentially does. Okay, and so you can think of a filter operation as like a matrix multiplication of an input to get an output. And so so here you can see that this matrix actually corresponds to one filter, which is 2 cross 2. Okay, so which means there are only 4 unique numbers here. Actually, this corresponds to 3 cross 3, I guess. 0, 1, and 2. Yeah, so this corresponds to a 3 cross 3 filter. Okay, it's taking so think of it on the left side, right? So what's going on is the top part is the input. So your input is like a 2 cross 2 slice, okay, 2 cross 2 matrix, and the bottom part is a 4 cross 4 matrix. Okay, how am I going from 2 cross 2 matrix to 4 cross 4 matrix? Is via, if you don't have to think in terms of matrices, the 2 cross 2 can be vectorized into 4-dimensional vector, and 4 cross 4 can be vectorized into 16-dimensional vector. So going from a 4-dimensional vector to a 16-dimensional vector. How do I do that? Of course, I need to have 16 rows and 4 columns, and as long as I have that, then I can go from here to here. And the 16 rows 4 column matrix is kind of parameterized by only 9 numbers. Okay, only by a 3 cross 3 matrix, and those 9 numbers are just spread out here, but they basically correspond to a filter which is 3 cross 3 size. Okay. So just kind of really unraveling that it's not hard to go from a lower dimension to higher dimension. Of course, there has to be some information in the input itself, and there has to be some information in the filter itself to kind of produce a, let's say, think of an image, right? So there is some information in the weights, some information in the input to produce a nice potentially an image. Okay. So we saw that, and then we kind of briefly motivated. We can always, and so the next couple of slides were just talking about, hey, if you have a vector image pair, I can always figure out the weights such that given a vector, I can produce the image. Okay, it's like you basically are trying to remember. Okay, so for example, given this vector, the vector multiplications, eventually, there's some information about this whole image somewhere, and so that eventually you kind of get image itself as the output. So you can do that, right? So this is just to motivate that going from vector to an image can be kind of remembered in the network. So you can remember this target image in the network, and whenever you pass this input of, let's say, vector once, you can output that image. Okay, so it's like literally, so it's as simple as saying, hey, each number here, let me just remember as a weight of my neuron, and then whenever this vector is input, I can just pick up that weight and just output that as is. You can do that. Okay? It's conceptual. And then if you can transform a single vector to an image, now you can talk about, hey, what if I had what if I don't know what the vector itself should be? And so then I can create a like a kind of a complementary network, so that I can pass the original image that produces a vector, and that vector pass through the decoder produces the original image. Okay? This is the idea, where you are now losing control on what the exact vector should be on the latent space. So you're only saying, hey, I only have 2 networks, and as long as you can compress and decompress, and I can get high quality image, then that's what I want. Okay, that's the auto encoding going on here. Okay. So that's so this concept is represented here in the diagram at the bottom, where you have an input data x, which is typically an image, goes to a smaller, typically a smaller vector z, typically a vector, and then that is reconstructed using a decoder, like the transpose convolutional network that we saw, to an image. And then you can really worry about how to tune the decoder and the encoder such that this reconstruction is high quality. Okay. So this is really, I mean, if you can think of even PCA as doing the same. Actually, PCA is going from some input vector to a low dimensional principal components vector um, corresponding to each data point, and then from the principal components you can actually reconstruct the original vector. Okay, it's just going to be low quality because PCA, if you only pick like a few components, then it's going to lose some information. Okay, it only keeps the directions of highest variance. If you decide to do so. And so PCA is exactly this, right? So going from original data point to smaller data point to a bigger data point. Okay, so what is it called? Reduce dimensionality, and then bring up the dimensionality to see if it is actually high quality reduction operation going on, right? So that's autoencoder. Okay, this is exactly an autoencoder, and you can do this for vectors, you can do this for images, you can do this for graphs. Okay, it's all what changes is the encoder decoder architecture. For images, we saw the con layers and transforms, decon layers basically. But for graphs, it will be what I call graph convolution layers. If it's a regular neural network, let's say it could be a feed forward network. This encoder could be just a one feed forward layer or two feed forward layers. Okay. In fact, I might have mentioned this last time as well. If the encoder and decoder are just single layer neural networks, okay, so which means that they're just one feed forward layer, then it's almost the same as PCA, except for one change. In PCA, what happens is the principal component directions are orthogonal. Here, if you solve this problem of like trying to minimize keep the reconstruction quality high, but only use one feed forward layer and one feed forward layer for both encoder and decoder, then it's just that the orthogonality is not maintained because it's not imposed here. But otherwise, it's the same type of linear like changing the projecting a vector into a lower dimensional space, linear projection such that you retain reconstruction quality. Okay. And so no labels. That's, I guess, unsupervised learning in the sense that your loss is just dependent on the input data. Okay, x only. So typically you choose an L2 loss function for real numbers, but you could change the loss to other variants depending on your application. Okay. So this is our autoencoder, and the problem with this is so remember this whole lecture and the last lecture was about, hey, I want to create new objects for sampling. Okay, but this is about compression. Really, autoencoder is all about only compression or dimensional reduction. It's not about generating new data points. Okay. Yeah, I guess so autoencoders cannot really generate new samples because I can compress, maybe my data is highly, there's a lot of, like, for example, if I take a lot of images and then the background is all the same, it's just maybe a subject is changing from one image to the other, then a lot of compression can happen. Okay, but it cannot really generalize in the sense that you cannot create a new sample, for example, of a new person standing with the same background, for example. So really, and so we need to fix that, and so for that we need a generative model, really, which is because we want to generate something, we need to have something from which we can, there has to be randomness, and there has to be some transformation of the randomness to produce something new, okay, some new sample. And so variational autoencoders are an extension of autoencoding to kind of deal with this generation idea. So because the goal happens to be, we want to generate new things. So it's a probabilistic extension. And so it's an example, as I said, of the class of what are called graphical models. Okay, so graphical models are just generative models where there is a joint distribution between all the relevant objects. Like, the basically relevant objects are going to be kind of defined as random variables or random objects, and there's going to be joint distribution on them, or whatever distribution on them. A graphical model just means that the distribution can be represented as a graph. Okay. Which means that if there are random variables, the random variables will be nodes, and then there will be links between those random variables, trying to say that, hey, they're related to each other or not. Okay. We'll see that the graphical model for a variational encoder, at least in these slides, is actually very simple. It's two nodes and one edge. Okay, and so it's a very simple graph with two nodes and one edge. But that shouldn't kind of restrict you. There are lots of graphs with lots of nodes and a lot of edges, but we'll not look at that here. It has connections to causal inference. I don't know if any of you are gonna do causal inference course anytime, but causal inference is one area where you see graphs, where you say one quantity is related to the other quantity, and these graphs encode what are called conditional independence assumptions that you're making about the system. Okay, but that's fine. So the idea is basically to make the latent space. If you remember the green bar in our illustrations before, to kind of say that the latent space kind of corresponds to some random variable, because some random variable is going to take values in that latent dimension, whatever 10 dimension, 100 dimension. So that's going to be random. And in particular, we're going to say that it's going to be a Gaussian distribution with mean zero and variance unit. So mean zero and variance being identity matrix. So if it's 10 dimensional, Z is 10 dimensional, then we'll say that Z has to be zero mean and with a diagonal matrix with with 10 cross 10 diagonal matrix basically. Okay. So that's the assumption we want to make. Okay. So now we said, hey, Z is now a random variable. It has to be Gaussian. That means that X is also going to be a random variable, and in fact, that's exactly what we want, because we want X's, which are, let's say, images. We want to think of a distribution over images. Right? So X has to be like a random variable as well. Okay. And so the idea for the generative process is that we'll sample from Z. Okay, we'll first get a sample from Z, and then pass it through kind of a decoder, and then maybe there's extra randomness, maybe not, and then we'll get an X out. Okay, so there is some source of randomness from which we transformed, and we got a derived random variable basically, and then that's a sample. Okay. So there are a couple of changes needed to kind of deal with this probabilistic or at least randomness. Okay. One at the architecture level, one at the loss function level. So what we're going to do is first talk about just the just what are these two changes, and then kind of really look at the derivation needed for the loss function definition. Okay, so we'll just mention what the loss function is in the next slide, but we'll not talk about how we got there. We'll talk about how we got there in like 3-4 slides. Okay. So let's think of like autoencoder had just the squared loss, the reconstruction loss. Okay. Now variational autoencoder will also have a loss function, which we'll try to minimize. Okay, to build the parameters to tune the parameters of the encoder decoder. We'll see the architecture in a second. It's very similar, but the loss will have now an extra term. Okay, so the usual loss that we saw, L2 loss, is called reconstruction loss. Okay, that will be very similar to before. But there's going to be one more loss, which is going to be called latent loss. Okay, this is a loss related to because we are imposing this particular randomness, random variable definitions, right, to our model, and so there's going to be what is called latent loss. Okay, and latent just means it's a loss related to the latent random variable. Okay, the Z random variable, and so the loss is about how far the Gaussian assumption, how far the Gaussian distribution is on Z, which is what we assume. We want the Gaussian distribution with zero mean and identity variance. Is how far is it from the distribution that we get from the encoder? Okay. So we'll see what this is in 2 slides. But basically, it's a way to quantify. Hey, I want to tune the parameters of my autoencoder like network such that there's a reconstruction error, which I want to minimize. But I also want to minimize that encoder is going from X to Z, right? And so that's going to kind of impose some sort of a conditional distribution on Z. That should be not too far away from the distribution of Z that I would prefer, which is the standard Gaussian distribution. So there's some distance there, and so I will tune the encoder such that it produces things which are close to that. Okay. So we'll look at that, and I think last time I briefly introduced. Briefly introduce the notion of entropy, but before that, what is the change in the architecture? The architecture is going to be has to have randomness, and so the only place but in particular we said Z is random. So how do we make Z random? Now what we do is the encoder network, instead of producing a single Z vector, is going to produce 2 vectors. Okay, it's going to produce a mean vector and a standard deviation vector. Okay, so standard deviation vector, remember, we only care about kind of Z to be Gaussian with zero mean and the identity matrix. So the only relevant numbers are on the diagonal, and how many diagonal numbers are going to be there? It's exactly the number of exactly going to be the dimension of Z, which means that if I can produce a mean vector and a standard deviation vector, let's say 10 dimension and 10 dimension each, those two parameterize a Gaussian distribution, right? Because I can take the mean vector and just say, hey, that's a mean vector. Standard deviation vector, I can just diagonalize it to say, hey, this is the variance matrix or standard deviation matrix, and from which I can sample the Z itself, sample a Z vector. Okay, so from these two, blue and yellow, I can sample a Z. That's the green thing, and then I can pass that as usual to the decoder network. Okay. I can also add extra randomness here, and we'll see that in maybe a couple of slides, but that's not super important at this point. Okay. So the main change is basically that we had to deal with randomness. Architecture side, we kind of made the forward pass a little bit different, because the forward pass for the encoder is just producing two vectors. That's deterministic computation. But after that, there's a coin flipping exercise going on. There's some sampling going on. Like I need to sample from this particular Gaussian with this mean and this variance. And then I'm continuing my forward pass. Okay. But although there's a sampling step, the backdrop is not supposed to be complicated, because once you know how the numbers are computed, you can always go back. Okay. So this should not phase you, and if it does, then I would say I want to assure you that there are ways, people have figured out ways to do backdrop when there is a sampling step involved. Okay. So it's not a in particular, it's called reparameterization trick. Actually, we'll see that in the VAE code in a second. But that's a change in the architecture. Okay. So why the sampling, right? In fact, remember, autoencoder is only about compression or dimensional reduction. It's not really about sampling. And variation autoencoder is really about, I want to create samples. Okay. So on the sampling step that you saw at the Z is exactly allows for generalization, because there's a noise being added, right? So going from encoder, so original image, to the reconstructed image, there's a noise being added because you're sampling at the level Z. So that makes the network more robust. Okay, it really has to learn the common patterns. Okay, so it's not just compressing, it's not just remembering training data, because that compression is all about just remembering as much as possible of your original data, right? That's what compression is, with the least number of numbers. So that's kind of something is what is allowing for generalization. And once we have trained, we can sample from Gaussian, pass it to the decoder, and then maybe one more sample if needed, but basically get an image. Okay. So here are some examples. You can see sample data during training, left and center, compared to the original data. So it's actually original data is on the right. Okay. And you can see the sample data early on during the training and later on during the training. Okay. So early on during training, so what is the sampling going on? Here we have encoder and decoder has frozen. In fact, for sampling, we only need the decoder. What we do is draw a Gaussian, pass it to the decoder, and get an image. Okay? And that image is like one cell here. Okay. And most of the images you can see are kind of either 9 or 0. Basically, that's what's going on. But once you train the encoder decoder, we a little bit few more epochs or something. Basically, you get a generated image like this. Now you may say, hey, is this generated image, or it could be one of the examples in my training data? Well, I mean, there could be a correspondence between this and training data, but the idea is this is really generated from the decoder and it's generalizable. Okay, and I'll talk about generalization maybe a few more slides from now. Like why that it really can create slightly different way, slightly different ones, slightly different 8s, slightly different 3s as desired. Okay, it's really not remembering just training data. Okay. So did I miss the definition of yeah, okay. So before we go into the derivation, I want to just switch and talk about. So this is from PyTorch's examples directory. Okay. So I just want to show you how the VAE's definition looks like. Okay. So it's not complicated, but I think by now, and I'm sure in assignment 3, you're looking at small such nn.module definitions. So this VAE actually has it's using these many parts for the encoder. Okay, so basically 3 fully connected layers for encoder and 2 fully connected layers for decoder. Okay, it's going from 784 dimensions, which is exactly mness is 784 dimensions, to a 20-dimensional Z vector. Okay, so how are you doing that? So you get the original image. Okay, passes is the first fully connected layer. So you can look at the encoding. Passes the first fully connected layer. Okay, then apply a nonlinearity. You get a hidden vector, right? Now, given that hidden vector, remember we need to produce a mean vector and a standard deviation vector. And so we are doing that. Okay, so we are passing the same hidden vector to something that will produce the mean vector, and something will produce the standard deviation vector, and both are 20 dimensional. You can see that 2, 1 and 2, 2, the output dimension is 20, right? So it's producing the two vectors. Once you do that, there is a so that's the step. Okay, so think of the forward pass is you're kind of doing the you're doing the encoding step. Get to the mean and the standard deviation. And in fact, the standard deviation, if you remember, standard deviations are very positive. Okay, so but if it's fully connected layer, it can produce anything. It could be producing negative numbers. So you just think of the output of the standard deviation to be the log of the standard deviation. Okay, so log of standard deviation can be negative or positive, but then you do an e to the power operation, then whatever, even if it's a negative number, it's going to be positive. Okay, so that's why it's called log variance here. So you produce two vectors, okay, which are 20 dimensional. Then you pass it to a step called reparameterize. Okay, so this is exactly the sampling step. You can see that in reparameterize step is just doing an exponentiation of the log var to get the actual standard deviations. It's calling a random, random, okay, random function to get a sample, and it's actually producing a sample with zero mean and identity variance, and then just shifting the mean and changing the variance so that it's actually the variance and mean that we want about. Okay, so this is just the sampling step. Okay? 53 to 56. And then once you sample Z, then you just move forward. So you actually do the decoding. Here it's already returning Z, the Z related things, but just decode it. And decode is just apply a fully connected layer and apply nonlinearity, and then apply another fully connected layer, and then apply a sigmoid operation. So here we're trying to decode and get the original MNIST image, actually 784 dimensional image, or here is a vector, and then you can reorder them so that you can get a 28 cross 28 image. So is it clear? So this is it. This is exactly what we saw in the architecture. This architecture, this part. Okay. Encoder and decoder were just fully connected layers here in that example, which you can do. You don't have to use decon and all that stuff that we're doing here. But now let's talk about some derivation of. So what is left? Okay, so we defined the architecture. We said loss has to have reconstruction and some latent loss. Okay, and that's what is left. Okay, so we just, to complete the picture, we just have to talk about what is the right loss function and why did we get there. Okay, because it's not going to be just reconstruction loss that we saw earlier. So you will see that the loss is a very principled objective function that you can get to. Okay, and generally it's going to be maximize the likelihood. Okay, the moment you have a graphical model, and generally if you want to fit the parameters of this graphical model, you have to maximize the likelihood of the data given the model, right? So typically it's maximize likelihood, but you'll see that maximizing likelihood is a little bit hard, and so there's some approximations that folks do here. Okay. So what is a model, right? The model is really about two random variables, x and z. So it's if you think of a graphical model, there are only two random variables, and there's an edge from the latent random variable to the observed random variable. X is observed, z is not observed. Okay, in my data. And what we want to estimate is some parameters theta. Let's call it theta star, which parameterizes the joint distribution between x and z. Okay, so in fact, joint distribution between x and z, think of it as p of theta star of x comma z. Okay, that you can factorize as p of theta star of z times p of theta star of x given z. Right? I mean, it's just a total probability law or just a definition of conditional probability. So we basically want this guy and this guy. Okay, so those are the parameters that we want to ideally learn, okay, for this model. And but we will do a couple of fixes here. We're going to first assume that this guy is actually just Gaussian. Okay, so p of z, we'll kind of assume that it's Gaussian. Okay, this is an assumption in this model. You can certainly change the assumption to some other model, some other distribution if you want. It's going to be a slightly different VAE. Okay, so we're going to assume that it's Gaussian, and p of x given z, at least part of it or fully, can be defined by a neural network. Okay, this is a decoder part. Okay, p of x given z is going to be a decoder network. Okay, and so since if I told you this is Gaussian and this is a neural network, right? So of course x is a derived random variable here. You can already say, hey, if I know these two, I know what is the p of x comma z. I know the joint distribution. If I tell you the marginal of one random variable and then the conditional probability of the other random variable given this original random variable, you know the joint distribution. If I know the joint distribution, I can integrate out the random variable that I don't care about, which is the latent random variable. If I integrate with respect to z, then whatever I'm left with is just the marginal distribution over x. Okay, the marginal distribution over x. And p theta of x is exactly the likelihood. Marginal distribution of x is exactly the is the probability of x, which is exactly likelihood. Likelihood and probability of x is the same thing. Okay, and so of course probability of x is a function of theta because these are all functions of theta, depend on theta. And so I want to maximize the likelihood of the data by figuring out what is the best theta that kind of maximizes the likelihood. Okay, that's maximum likelihood estimation, right? Any questions here? Because if this is not clear, then the next couple of slides will not be clear. Okay, so now let's we want to maximize the likelihood. Okay, but there is a problem. Okay? There is a problem, and we'll see that problem in a second. But I want to briefly mention, at least in the architecture, like at least at the block level, what's there's a couple of more bells and whistles here. One of them is that if you just focus on the right hand side for now, okay, ignore the left hand side for now. If you see, going from z to x, we said, hey, there's a decoder network. Okay, we said it's a neural network, right? It's parameterized by theta. We said, okay, so that's fine. But just like we did it with the encoder, we're going to also make the decoder such that decoder is going to produce a mean vector and a standard deviation vector. Okay, it's just an extra trick. You could say, hey, I don't need a mean vector and a standard deviation vector. I can just produce a directly output image. Here we are saying that let's produce a mean and a standard deviation, and then let they parameterize a normal distribution from which if I sample, that's the x. Okay, so now there are like two sources of randomness. One is like z is random, and then x is random given z, because given z, that's gonna parameterize the mean and covariance, and then from there x is drawn as a sample. Okay, okay, so that's just clarifies like one extra bell and whistle here, like one, that there's one more sampling going on. That's fine. Now, the more important or more interesting thing is what we're going to do is we're going to so we made the encoder probabilistic. So ignore this statement. We already discussed that we can make the encoder probabilistic. It was there in the architecture earlier, right? But we're gonna talk about an encoder now. So if you just look at the previous slide, there's no discussion of encoder. It's just, hey, there's two random variables. I know the joint distribution. I just want to maximize the likelihood, right? But you'll see that there will be a need for an encoder, because why do we need an encoder? Is exactly because we don't know z. We don't have the observation z. This is a data set where we only have x's, but we are saying, hey, our model is actually a joint distribution between a latent random variable and x's. Okay, and so for now, let's assume that we have an encoder part, and we'll see how that fits back in when we're trying to maximize likelihood. Okay, and in the architecture diagram that we saw 2 slides ago, there was an encoder anyway, right? So encoder is exactly this. Just think of the encoder also has another set of parameters p. Okay, so it's basically what the encoder is doing is going from x to z, and we already saw that it's going from x to some mean and covariance, and then you actually sample, and that's what gives you z, right? But the encoder network, let's say it's a network which is represented like this. Okay, q of phi of z given x. Okay, it's like a extra thing. For we're going to use it in a second to deal with this maximum likelihood problem. Okay, so when we're trying to maximize likelihood, we'll see there are some issues, so we'll fix it using this extra thing. Okay. In fact, let's and one last thing I want to introduce before we maximize likelihood and deal with some computation is the notion of KL divergence. Okay, just a recap. KL divergence. I don't know how many of you have seen it before. Have you guys seen it before? KL divergence. Okay, so just think of, okay, so this is a very abbreviated exposition here. So think of random variables are supposed to represent information. Okay, so the density function, so the probability mass function, let's say, is supposed to represent information. How like how likely is a particular, how likely is the random variable taking a particular value, right? The smaller the probability, there's more information. It's a kind of a informal way of saying it. Like, let's say tomorrow it's going to be sunny with 90 degrees weather. Okay, there could be a small probability for that, but there's a lot of information, a lot of like new information for an observer if that actually happens. And so negative log of that probability kind of represents that, hey, this is a highly informative outcome that can happen. Okay, why? Because p, if it's small, log of a really small number, remember p's are all less than 1. Log of a really small number is like really negative, and then minus of that is like really positive. So high information. Okay, low probability. And entropy is just the average information. Is just an expectation with respect to the density function x of x itself. It's like think of a uniform random variable. Okay? So uniform random variable is a random variable which, let's say, it takes 10 values. So each value is probability 1 by 10. Okay, then that uniform random variable has the highest entropy, because there's a lot of like uncertainty in like which event can happen. Okay, compare it with a random variable which like 99% one event can happen. Sorry, one of the values can be taken, and then remaining 9 values is like 0.00 something. Then that random variable, although the other outcomes are like very less likely. Okay, but in terms of the average, average randomness in that random variable, it's quite low, because there's one of the outcomes is like very, very likely. Okay, so entropy is again a measure of uncertainty in a distribution. Okay, like some distributions, like uniform distributions, are like all over the place, anything can happen, and then non-uniform distributions, like, okay, some of the outputs are like very likely. Okay, so that's the definition of entropy. It's just a measure of things, and it kind of plays a central role in wireless communications and all the how cell phones work and all that, at least in the engineering realm. For us, it helps. This expression is kind of very similar to another notion which is called KL divergence. And this is there's only one reason why I'm introducing it, because we need KL divergence in the next slide for our maximum likelihood estimation. So KL divergence is a measure of dissimilarity between two distributions. Okay, so if you have a probability mass function, another probability mass function, you can say, hey, element wise I can compare, hey, how off they are from each other. Okay, that's one measure. But KL divergence is a slightly different measure, also comparing how two distributions are different from each other. Okay, and it has a very interesting expression. It's basically so KL divergence between P and Q, where P and Q are two probability mass functions. Just think of this, that's a 10 outcome probability mass functions. Is just it's like a sum of P of x log P of x by Q of x, and you can see that that expression is very similar to here. Okay, this expression is like sum of P of x log P of x, and you can see sum of P of x log P of x here, extra minus sign and a Q of x there. But so KL divergence is a measure of how dissimilar these distributions are. Turns out that if the two distributions are very dissimilar, this number is high. If they are very similar to each other, this number is low. In fact, this number is this KL divergence measure, okay, because it's taking two distributions input and producing a number as an output. It's lower bounded by 0, in the sense that it's like a loss function. It's 0 if two distributions are the same, and if two distributions, the moment they are very different to each other, it just blows up, like it could be 10 units, 50 units, whatever it is. Okay, so it's in some sense it's like a distance or a loss measure. Okay, how different the distributions are. Why I'm introducing this is because, remember, there was a latent loss, which is like which is something about the Gaussian distribution assumption on the z versus an approximation to that. Okay, so there's going to be an approximation to that driven by the encoder part, and so this is a measure to kind of compare those two. Okay? But anyway, so let's actually come back to now, how do we deal with maximizing likelihood? Okay, so let's ignore the right hand side for now. Okay, left hand side, let's just think of the left hand side, right? For a given data point xi, or for a given image xi, okay, you may ask, like, what is the right theta for which xi is the most likely outcome? Okay, so that's the likelihood of the data point xi. Okay, log of that is just a log likelihood. Okay, so the right hand side is just a log likelihood of a particular data point, and now if you average over all the data points, The left hand side is just the likelihood of your entire data. Okay, but for now let's just focus on one data point. So left hand side is the likelihood of the data point, but maximizing this is hard. Okay, and that's the crux of all this page of derivations. Why is that? Is because if you look at this, if you want to maximize this term, there is an integration with respect to z involved. Okay, and so this integration, it's unclear how to do it. Okay, computationally, even computationally, it's unclear how to do it in a good way, because z could be 10 dimension, 100 dimension, whatever it is. So it's unclear how to maximize over theta. Okay, so remember, you have an objective function. Like most of our previous models, if you remember last functions, the objective functions don't have an integral term. So it's like you can easily find what is the loss, take the gradient, update, okay, your parameters. But here, if you, for a given current theta, if you want to compute the loss, that itself involves integration, and you want to take the gradient of loss with respect to theta, that seems even more complicated. Okay? So this term is not easy to compute. Okay, this integration. So that's what leads us to some bunch of steps. What although I'll talk about the bunch of steps, what it will lead to at the end is just a approximation to the likelihood function. So instead of maximizing likelihood, after a bunch of steps, all we're going to do is maximize something else, some proxy. Okay, that something else hopefully is connected to this, and that's why there's a bunch of steps involved. Okay, but that's what we're going to do. Okay, and this pattern is not specific to variational autoencoder. The word variational is actually related to this variational approximation. Variational just means optimization. Okay, so there is going to be clearly there's going to be optimization because we are going to maximize likelihood. That's an optimization objective. But variational autoencoder, variational approximation, okay, just means I'm going to switch out the original objective with a slightly different optimization objective. Okay? So that's how the terminology variational comes from. It has its own history, but for us informally, it just means there's an approximation going on, and there's an optimization step, involved, because we want to maximize likelihood. Okay? So let's look at the steps, only because they're not, there's nothing deep with those steps. Okay, but it's a nice set of tricks to know. First step is you have the original likelihood. It's a function of theta. What if I take an expectation with respect to an unrelated random variable? Okay, so if you had if your original random variable is x and I want to take an expectation with respect to a random variable y, there is no effect, right? I mean, there is no relationship between them. So it's actually a constant with respect to the random variable z here. This whole thing has nothing to do with z. I'm taking expectation with respect to z, and also drawn from a particular distribution. Okay, this has no impact on this thing inside. Okay, so it's like taking expectation of 1. I mean, expectation of 1, whether you take an expectation with respect to one random variable, other random variable, it's 1. Okay, so the first step is just useless. The next step is this marginal distribution over x. We're going to break it down into 3 terms. Okay, we're going to break it down in 3 terms. Why are we getting 3 terms? It's just a base rule. If you want to eyeball it, if you look at this marginal distribution times the denominator, probability of x times probability of z given x is just a joint probability of x and z. Numerator is just probability of x given z times probability of z. That's also a joint distribution between x and z. Okay, so all we're doing is replace the marginal distribution by 3 terms by just following base rule. Nothing has changed. Okay, now because now we have 3 terms, and log of a divided by b, if you remember, is just log of a minus log of b, right? So we're going to make use of that property. But before that, let me add a couple of more terms here. Those terms are just constants. Okay, so if I multiply and divide by the same number, that doesn't change anything. Okay, inside the log. Okay, this whole thing is inside the log here. I didn't put a bracket, but I multiply and divide by something. Okay, all these choices are, by the way, it's not like when you're doing it forward pass you can figure out these choices. It's just a simplification that has happened over the years when people figured out how to how to motivate this. Okay, this is just a way to explain it, but it's by trial and error how people did it. Okay, so we multiply and divide by a constant. Okay, phi of z given x. Okay, and it's conspicuously the same as this expectation here, but anyway, it's multiply and divide by the same thing, so it doesn't matter. Now we use that log, log of a divided by b is log of a minus log of b expression. And so let's extract our terms. So first term we'll say is that probability of x given z. Okay, so that's the first term. And then what we'll do is take pairs of these two terms. Okay, pairs of these two terms. So let's take P of z and Q of z, P of z and Q of z with the conditional thing as one pair, and then P theta of z given x and Q P of z given x as one more pair. So there's nothing, it's just two pairs, and then log by definition, splits like this. Okay. Why is there a minus? Is because the Q was in the denominator and P was in the top, and it's just flipped in this term. Okay, there's nothing else going on. So okay, so we got three terms, and pretty much we are done. Okay, this is a kind of the heaviest slide for this session, this or in general the whole course. So what we're going to do is, just now we are just recollecting that, hey, KL divergence has a very similar term. It's an expectation over Q phi of z, log of Q phi of z divided by phi some other distribution is just the KL divergence between that and something else. Similarly, the second term is also some KL divergence between the numerator and the denominator. Okay, so there's nothing, it's just a definition of KL divergence we just plugged in there. Okay, there's so once we did that, what we can do is, all we did is go from the original log likelihood of an ith example to these three terms. Okay, now what we can do is what we can do is actually now try to maximize these three terms. Okay, by in fact, instead of optimizing all these three terms, what we're going to do is we'll drop one of the terms. Okay, we know that the KL divergence between two distributions is always positive. So if I drop the third term, okay, then the first two terms are a lower bound. Okay, they are a lower bound to the original left hand side. So left hand side was equal to three terms. The last term is always positive. So if I remove it, then the remaining terms are just a lower bound for the original term. Okay, so drop the last term, and that we can drop because KL divergence is positive. Okay. Now this thing here, which is then the first two terms, are called the variational lower bound or called the evidence lower bound. ELBO, ELBO is the acronym that you'll see. And so this is the second strategy in this whole variation optimization business. Okay, to get to a proxy which underestimates or actually lower bounds the original log likelihood term. Okay, so these are two terms here. Now what we can do is we want to maximize likelihood, remember, so we want to maximize this term. Okay, let's call this term L, script L. Then we just want to maximize this with respect to whatever parameters are in place, which is theta and phi. Okay, so theta and phi are things that we can choose, so we're going to choose them such that this thing is maximized. Okay, so this first term here is actually just a reconstruction error. So p theta of xi given z is just the reconstruction error if you're going to assume the normal approximation. Okay, so it's just, if you think of a normal distribution, log of the normal distribution, remember we did this for normal distributions. If you think of maximizing the likelihood of normal distribution, it just becomes the square type of loss, square loss, right? The same trick happening here. The first term is actually turns out to be the reconstruction error, and the second term is exactly some sort of a KL divergence, and this is exactly the latent loss that I was talking about. Okay, so we want to maximize this thing. Okay, so the first term happens to be negative of square loss. So whether you can minimize this square loss plus a KL divergence, or you can maximize the negative of square loss minus the KL divergence. KL divergence is going to be more if these two are different. Okay, so that's how we get to a principled proxy for the original likelihood function. But this is just I guess a second order issue. I mean, the first order issue is as long as you agree that we can have a distribution and we can maximize the likelihood, then this is fine. Okay, at this point, this is fine for describing what you want to do, how you want to get the parameters. But because this thing is hard, we did the evidence lower bound. We computed the evidence lower bound, and we just maximized that. Okay. Let's come back. Okay, let's put everything together, because the derivation is just to show you that, hey, the original objective is hard, likelihood objective is hard. We want to do something else. And I want to show you that because there are many other models, including Gaussian mixture models, for example, where you can also use not variational approximation, but when you use EM, you are basically doing like a proxy for the original likelihood function. Okay. So let's put things together. So basically input data X is going to produce Z through the sampling through a normal distribution. Z, you're going to get again a mean and a standard deviation, and you have a distribution over X from which you're going to get an X, and that's the X hat that you produce. Okay. So there's an encoder encoding to Z and then Z to a decoder. Okay. So that's the architecture, and the loss function is exactly what we saw: a reconstruction plus a KL divergence. I say plus because if you think of loss, then it's not maximizing evidence lower bound, but minimizing the negative evidence lower bound. Okay, that's where you'll have a plus KL divergence loss. Any questions about this? It is a little bit heavy for the first time you're seeing it, but at least a high level it should be clear, like what the moving parts are. Okay, so next couple of minutes, I'm just going to wrap up VAEs, and then we can maybe take a break. So, I mean, whole point of VAE was to create new samples, generalize and not just do compression or like dimensional reduction. And so once you train the VAE, you kind of ignore the encoder because, very similar to a few times we try to ignore the encoder. So ignore the encoder, and then just how do you now create new samples? You kind of assumed and you kind of imposed this constraint that Z has to be, the marginal distribution of Z has to be normal with a zero mean and identity covariance matrix. So that kind of gets imposed as much as possible. And so you just sample from Z, which is like a unit normal distribution. Then pass it through the decoder, you get a mean vector and a log var thing. And then from those two, you can those two parameters another normal distribution from which you can get a sample. Okay, that's it. So how can that sample have image-like features? Is exactly because the decoder network will have that information, okay, the general pattern of how images should look like. Okay, and so this was proposed in 2014, so it's only 8 years old, okay, relatively speaking. Gives you a sense of like how all these architectures we're seeing, many of them are kind of recent or at least have been robustified in recent years. Okay, some of them are older, but they've come into forefront in the past few years only. So anyway, so this is the paper that proposes this, and here you can see now the generalization aspect that I was talking about. Okay, so what you can see is basically images produced by the variational encoder. This is literally after training. You drop the encoder, you ignore the training data now. All you're doing is sample a normal distribution Z and then passing through the decoder and just producing images. And you can see that images are not that good because, of course, limitations of this technique that it's very hard to produce a new in a very realistic looking face from this architecture, at least on this particular data set. But you can see that if you saw the this person does not exist, you can see how much you can get. Of course, if you have to do a lot more extra tricks to get there. But these are the generated images. Even for CIFAR10, these are like, sorry, these are not exactly. If you zoom in and see, they don't exactly correspond to anything. I mean, they're not exactly perfect. Okay. Let's focus now on the left-hand side, where you can see what we're doing is now left-hand side is a different data set. It's the MNIST data set. Okay, so an MNIST data set. What we're trying to do is take the Z, do this variational encoder, build the variational encoder, and now what we're doing is instead of sampling from Z, we're just picking two Z dimensions. Okay, like in two coordinates of Z. Okay, for simplicity, let's assume that Z was actually two dimensions. Okay, for simplicity, for MNIST data. Now what we're doing is vary one coordinate and vary another coordinate. Vary as in like really do a grid search. Okay, so we're saying, hey, let's pick Z1 to be 0.1, Z2 to be 0.1. Let's pick Z1 to be 0.2, Z2 to be 0.2, and so on. So just the grid search, and you can see how the output changes. So for small values of Z1, Z2, there is some something like 7. When Z2 increases, it becomes a 1. When Z1 increases, this becomes a 9, and then a 6, and so on. Okay, so you can really see by moving around in the latent space, you can get a sense of how the numbers kind of are next to each other. Okay, and this is something you cannot do with vanilla autoencoder. You can do it, but you don't expect this type of result. Okay, because they are focused only on compression. They're not really focused on generalization like this. So this is how you would get potentially new images. Like you can really see that these like something which is between 7 and 6 may not be, 7 and 1 may not be in the training data, but it's there here. Any questions of variational encoder? If not, let's take a break for 10 minutes and resume at 4:45. Okay, so welcome back. So what we'll do next is look at a slightly different object from which we want to sample images, and that StyleGAN was an example of this. StyleGAN 2 was an example of this, and it's called generative adversarial networks. The difference is going to be, I mean, there's going to be quite a bit of similarity on the architecture side, but also some differences. Also the difference is going to be in terms of the objective function. Okay, it's a non-standard objective, non-standard objective function that you might not have seen in statistical approaches. Okay, it's not maximizing likelihood. It's not minimizing some simple square loss directly with the data. It's doing something different. Okay, and so we'll see what the architecture is and what the loss is. Okay, so so if you drop the adversarial word, it's generative networks is the name. Generative networks just mean you again want to generate some samples. Okay, adversarial is in the name because of the loss function. Loss function happens to have a what is called a minimax form, which means that if you think of parameters, right? If you go back to VAE, there were two parameters, okay, theta and phi. Phi was for encoder and theta was for decoder, and we were simultaneously maximizing with respect to both these parameters when we're trying to maximize the evidence lower bound. Okay, so remember, if we're trying to maximize the likelihood or the evidence lower bound, we were trying to maximize with respect to both these parameters. Okay, the adversarial name here just corresponds to the fact that when you're trying to do an optimization, appropriate objective optimization here, if we're going to optimize, we're going to maximize with respect to one parameters and we're going to minimize with respect to the other parameters. So there is a adversarial or the opposite need here. It's like maximize with one parameters and minimize with respect to another set of parameters. Okay, so that's why it's called adversarial here. We'll see the expression in a second. So what is GAN, right? So the idea is to kind of ignore any probabilistic notion. So in VAEs, we said Z is a random variable, X is a random variable, Z is in fact a Gaussian random variable, and all that. Okay, we're gonna get rid of all probabilistic notions. So it's like no assumptions on something being a distribution or not. But still, we want to get an object from which we can sample. Okay, of course, we're going to use some randomness, but we're going to drop this notion of a distribution or joint distribution or conditional distribution. Okay, we're going to kind of drop those notions. Okay, so we're going to take a game theoretic approach for defining the architecture, defining the system, as well as the defining the objective function. Okay, so what is the game theoretic approach? So there are going to be two players or two networks, very similar to VAEs, where there was an encoder or a decoder. There were two things. Here, there's going to be two players. Okay, so the first player, we're going to call them by the letter D. Okay, so player D, okay, or network D. Okay, what should it do? It's going to take. It's basically like a CNN. Okay, it's going to take an image. If the image is a part of my data, then that CNN or whatever, that D tries to produce a score. It's going to be a binary classifier essentially. So it produces two scores. So it's gonna, or just for simplicity, assume that it's going to only produce one score. So let's say it's like a type of regression problem. I'll just think of a softmax after that. So D of X should produce a number which is close to 1. Okay. So for a data in my for an image in my data set, it should produce a number which is close to 1. Okay, but the same network or player or function, if I input anything else, okay, any other X, okay, instead of X, some fake X, okay, something which is not in my data set, it should produce a number which is close to 0. That's the objective. So if you look at only this part from this point on, so ignore the bottom 3 blocks for now. Just look at D, right? So on the right side, So D tries to make whatever it's given as input, it's called G of Z, to be close to 0. Okay, so it tries to make D of X close to 1 and D of G of Z close to 0. Okay. So these three, I'm just focusing on these three cells and these two cells, and ignore the last two lines here. So D should make whatever output in the second scenario close to 0. So whatever input it's gotten close to 0. Okay. Now what is the input that it's gotten? You start with some noise, which is noise just means some flip a coin or basically draw a sample from a Gaussian distribution. Okay, that's noise. So get a noise. Now this is the second player G. Okay, so G is a function or a player or a network. Network means like neural network, right? So takes Z as an input and produces an X. Okay, so it produces an X, and so G is trying to produce an X which is as close to realistic looking images as the original data. Okay, so it's trying to produce images. There's actually original data which is a bunch of images, so it's also trying to produce images which look realistic. Okay, and then that's being passed to D, and so therefore D's objective is, hey, this image is not from my data set, so I want to make it close to 0. And then G's objective is to create images such that D is trying to confuse it. D is going to be confused and it's going to produce an output 1. Okay, so I'm going to explain this again in a couple of times again. So basically GANs is about two adversaries. Okay, two adversaries just means opponents, or that's all it means. So there's a D network and a G network, and they are trying to kind of achieve some goals. Like D is trying to say, hey, it's trying to differentiate between real and fake images, real and non-real images, basically whatever is not there in the data. And then the second player G is trying to confuse the original the D player. Okay, so that's why it's opposite to D. Okay, D is trying to kind of identify, hey, this image is from G and not my original data, whereas G is trying to create an image which is as similar to original data as possible. So let's actually look at it from perspective of one-dimensional setting. Okay, so forget about networks. Okay, let's say there is a function G. Okay, which is parameterized by theta subscript G. Okay, theta subscript G are the parameters of this function G. It takes Z as an input. Z is a random variable. Just think of it as like a Gaussian distribution, one-dimensional Gaussian. And let's say X is an output that it produces. Okay. And what we want to do is, let's say that we have an original data. So let's focus on this figure here. So there is a Z random variable. Z, there's a Z random variable that takes some values in this, let's say on the real line. What is the G function doing? It's just producing a derived distribution on X, right? So if Z is a random variable and I apply a function, then I have a derived random variable that will have its own distribution, right? So let's say that distribution is on the X, it's also a real line. And let's say that distribution is in fact exactly equal to this green curve. Okay, that distribution is this green curve. Okay, now let's fixing that. Now let's say our original data is actually these dots. Okay, our data is these dots. Okay, this is the second thing. So there are two different components. G is a fixed function which is going from Z to a distribution like this green curve, and my original data, which is a curve like this. I don't have to draw a curve. I plotted all my points, and I can connect them together. And there's another distribution here. Now, what D is trying to do, the discriminator or the D function, it takes X as an input and says, hey, should the output be 0 or 1? Okay, or close to 0 or close to 1. Okay. So basically, what it wants to do is, if it's a black dot, if the data is actually from black dot, then it should be 1. If the data is from the green curve, then it should be 0. Okay, that's what it's trying to do. Okay. So if you can see that in this is actually a tough situation where the data and the green curve kind of overlapping the distributions. Okay, so that's why D may be, for even like data coming from the green curve, it may say 1. Okay. So it's a tough situation, but you can imagine two such peaks far away from each other. Then it's very clear, very easy to kind of D to say, hey, if data is coming from the something X less than something, then just say 1, and if X is greater than something else, say 0, right? So that's the kind of role the generator and discriminator are playing. Okay. Actually, I have several, I have like 2 more images trying to say the same thing. So if it's not clear, I'm going to repeat it again. So as I said, there are 2 players. One is called a generator, and that's why we're using the short form G. Another one is called discriminator, which is short form D. Okay, the generator network or whatever model G function is trying to fool the discriminator by generating real looking images. Okay, and this is exactly what we want at the end of this process. Okay, remember, we want a sampler from which we can sample new images, and so generator is the one which is eventually going to give us new images. Okay, but while training, we want to kind of still learn the parameters of the generator, but and so the generator objective now for training purposes is to fool the discriminator. And what is the discriminator going to do? Try to distinguish between real and non-real images, or real and fake images. What are real images? Real images are the images in my data, in my data set. Okay, and generate
Professor,
any data set. Yeah.
Is there a way to measure or like how realistic are the fake images?
Is there a way
to evaluate?
Sorry, can you repeat?
Yeah, is there a way to evaluate how realistic are the fake images?
Yeah, I mean, so way to measure the realism in the images once you already have a trained generator, you mean? So there is some objective function, okay, here, and we're gonna try to optimize that objective function. Okay, so of course, if the objective function is optimized to the fullest, then you should expect realistic images. Okay, but it's not that at any given point in the training time, during training, we can't. There's no objective measure to say some image is realistic and some image is not. Okay, that's because these are generated images. They may not have anything to do with the trained images. In fact, there's no. If there are 10 training images, sorry, the generated image may not. You don't even know which one it matches to. Okay, here. So it's not like reconstruction error that you can have in the VAE case. So let's look at it. So let's actually go a little bit more forward and let's come back to this question of whether can we know how realistic the images are. Okay, let's come back to that. So let me, again at the high level, discriminator network or function on the left side, it is getting input from real data. Sorry, on the left side is getting input from the generator network, whose input is random noise. Okay? From noise, its generator network is actually creating images, and those images should hopefully not look like real images from the perspective discriminator, so that it can discriminate that, hey, it's fake. If things are coming from here, it's fake. If things are coming from here, it's real. Okay. And real images are just my images from my training data. So the CIFAR 10, like 60,000 images or whatever that we have, those are the real images. Okay. So yeah, so the same picture that we saw in the previous slide with a little bit more annotation of Z is a latent random variable. G is that generator function whose parameters we need to learn. G of Z is a sample. Okay, this is a fake sample. Real world, if you just get one of the images, it's going to be a real sample. If you pass this one, so it's not like both are going in at the same time, but you can pick one of them as an input. So it's basically, from the discriminator's perspective, it's just supervised learning. Okay, so it knows that this sample is real. So you wanna kind of tune the discriminator such that, hey, this sample, the label is real, but this sample, the label is fake. Okay, so it's just a supervised to binary classification from the discriminator perspective. Okay, and so that's what so you're going to tune the parameters of the discriminator. Okay, so generator's perspective, it's trying to change its parameters such that whatever it produces, given a discriminator, is going to produce a number which is like close to what it would have produced for the real number, which is like close to 1, let's say. So now, is the architecture level information clear, like what's going on? Now we're going to talk about the objective function, and objective function is just going to be like a cross entropy loss type of thing. But I want to step to that before I don't want to step into that before it's clear like what is the architecture here. This is just for the training setup. Once your training is done, we don't care about all this stuff. We only care about this blue box, sorry, to generate new samples. Okay, so now let's look at the loss function. As I said, if you look at, actually, before going to the loss function, generator is trying to like how is generator going to tune itself? Because at the end of the day, as I said, the blue box is what is going to generate new realistic looking images. But this guy, its input is a random vector. Okay, so there's no information there, certainly. So all the information, all the tuning of weights that happens for this network is through some feedback, is through some loss, some gradients that flow. But the generator itself is never, when you're trying to flow the grade, when you're trying to improve the weights of the generator, it's not directly looking at the image, it's not directly looking at the training data at all. Okay? Somehow training data is influencing the weights of the discriminator, and then the weights of the discriminator are influencing the weights of the generator. Okay, so it's not, so in the VAE case, for every image there was a corresponding reconstructed image, and so the weights of the encoder and decoder were being tuned to ensure that this reconstructed image is close to the original image, because there was this. So but the generator case, it's not like that. Okay, so generator can produce whatever images. Information about real world images is captured in the discriminator such that that information can help deal with improving the images that the generator generates by changing its parameters. Okay, so it's a little bit kind of not straightforward way in which information is helping generator tune its parameters. So now let's look at the objective function. So both the generator and discriminator are going to have objectives. So think of two-player game, right? If you're playing chess, for example, you have an objective, your opponent will also have an objective. Both of you want to win, right? Both of you are optimizing for something. Scores, maximizing scores. So what? And since there are two players, this and their objectives are actually the opposite of each other. So think of a situation where if you score high, the other person has to score low. Okay. Or for example, if you win, the other person has to lose. Okay. Or maybe there's a fixed budget of scores, like a fixed budget of total score, like 1,000. And so if one guy gets 600 points, the other person can only get 500 points, for example. So that's called a minimax game. Okay. That's called a minimax game, or it's a game which has the adjective minimax. Just means one is minimizing, the other one is maximizing. Because at the end of the day, there is a constraint that both cannot, so both cannot have high scores, because for example, one can win, then that means the other one will lose. Or if it's a fixed budget of scores, if one gets 600, the other one will have to get 400. It cannot get, the other person cannot get 600. Okay. So it's opposing forces, adversarial. So now let's look at the, so as you can see, let's actually look at the last point. This J of G and J of D are just the objective functions of these two players. Okay, what they're trying to optimize for. Okay, so you can see that J of G is just a negative of J of D. Okay, which means that whatever score this first person, the discriminator gets, the generator scoring is just the negative of that. Okay, so you can see that the sum is actually 0. The budget is actually not 1,000 but 0. So one wins, the other one loses, basically. Okay, now let's focus on what is J of D. Okay, so what is the objective that the generator is trying to, so discriminator is trying to maximize? Is there's going to be two terms, one related to the real data, one related to the fake data. Okay, so the first term is related to the real data. Okay, in fact the first term is just the cross entropy loss. Okay, so it's a negative log of the whatever the probability that I'm saying for the real data. Remember, d of x is a number that I'm saying between 0 to 1 for real data. So if I say high number, let's say close to 1, then log of 1 is kind of 0, and so I don't lose any points. But if I say for real data, d of x is like close to 0, that means the log of d of x is like hugely negative, and the negative of negative is positive, so this number is going to blow up. If I give a 0 to a real image, then I'm gonna kind of incur a huge I guess loss. So okay, I should say these are losses, not scores. So don't think of these guys are trying to maximize, but trying to minimize for simplicity. Okay, so this is the first time is actually just the cross entropy loss for saying that for real images I have to get the label to be close to 1, or I have to get the output which is close to 1. Okay. Now the second term is exactly the opposite. Okay, so it's just, and you can see that here, whatever I produce for this image, I better produce so the second term is for fake images. Okay? For fake images, remember, I want to produce scores close to 0. So if d of x is close to 0, then log of 1 minus close to 0 is basically log of 1, so I don't lose any points. But if d of x is close to 1 for this fake image, then I'm in trouble, because if it's close to 1, then 1 minus 1 is kind of close to 0. So log of 0 is kind of minus infinity, and minus of minus infinity is plus infinity, so huge penalty. Okay, so it's basically just saying for real images get a number close to 1, for fake images get a number close to 0. Okay, that's all. And then j of g is just a negative of that. In fact, you can see that j of g, so g is only appearing in the second term. Okay, so because this has nothing to do with the generator. This is just, here's my training data and here's my parameters of my discriminator. So really the generator is only influencing the second term, because this x is being produced by the generator. Okay, so let me directly mention what is the best thing you can do, okay, in this minimax game. Okay? In this minimax game, the optimal strategy is actually quite simple, but also hard, and I'll tell you why it's simple. The optimal thing that the discriminator can do, okay, so if it's a minimax game, by the way, there's a notion of what is called an equilibrium. Okay, equilibrium is just a concept. I think some of you might have heard of Nash equilibrium. Okay, so that applies here as well. This is a zero-sum game. So equilibrium is just a kind of a value for both players. I mean, so kind of a strategy for both players. A strategy just means like their configuration. Just think of, in our case, it's just what is the discriminator parameters, what is the generator parameters. There will be parameters such that discriminator cannot improve its score unilaterally without discriminator cannot improve its score unilaterally, and neither can generator. Okay, so it's like a equilibrium, means it's like a stalemate. This is the best both of you can do, because if one changes their configuration of parameters, the other one can change and improve. Okay, so you cannot do better than this. Basically, it's like a stalemate. Okay? So the equilibrium strategy is actually just very simple things. For at any given x, you just have to, discriminators should produce a score for that x, which is probability or my data of that x divided by probability of the data of this x plus probability of model. Model just means that the generated model. So P of m corresponds to generator of x. Okay, so this is the this is the score that discriminator should produce for any given x. Now, without looking in this expression, it will be really hard to understand like why is this optimal strategy, right? For that, what you can do is actually just look at this expression. Okay, this expression, what you can do is when you say discriminator has to maximize this objective, sorry, a discriminator has to minimize this objective. Okay, because these are losses. I mean, you can take a negative and say, hey, you need to maximize, but let's say discriminator is trying to minimize this objective. Then you can see that discriminator can minimize for each x separately. So if discriminator can focus on each x separately, okay? At least conceptually, by which I mean that you can focus on, hey, given an x, how can a discriminator minimize this objective? You can ask. So that just looks like, if you look at this first term looks like negative log of some unknown. Let's call it w. Negative log of w minus log of 1 minus w. Okay, for a given x, for a given image, for a given image there is like these negatives are not important, because I'm gonna evaluate and set it equal to 0 to kind of take its derivative and set it equal to 0. So the first term is just going to be p of d of x times log of d of x. Second term is going to be minus p of m of x times log of 1 minus d of x, right? If you just focus on the particular x and forget about the expectation, right? Then I'm just saying, hey, you don't have to write d of x, and you can just think of d of x as like some w or something. Then it's just p of d of x times log of w minus p of m of x times log of 1 minus w. Okay, some fixed thing. Now you can take a derivative and set equal to 0. First derivative set equal to 0. And what is the derivative with respect to w? Okay. Then you can see that log of w, what is the derivative? It's 1 by w. And what is the log of 1 minus w? It's just minus 1 by 1 minus w. Okay. Now if you set it equal to 0, you will just get w is equal to this. Okay, so it's not a magic that we got this. This is just if you take the derivative of the loss and set equal to 0. So for every x, you will get d of x should be exactly this. Okay. If d of x is this, so if I tell you this is the best thing that d of x can do, like then for any given x, then what is the best thing that the generator can do? Okay. The optimal strategy for the generator is to set itself up. So generator, what is its parameters? P of m, Pm of x is its parameter. All it has to do is match whatever the data set is, right? So that's kind of intuitive, right? If generator is exactly the same as the data set, the data distribution, then discriminator cannot discriminate, and that you can directly see here in this picture. If this green curve is exactly overlapping with the black, how can the discriminator say it's 1 or 0? Like you cannot make discriminator cannot discriminate between the black curve and the green curve if they exactly overlap, and so discriminator is going to produce a value which is 1/2, right? It cannot say 1 or 0. It will say 1/2 because I don't know. I will have to flip a coin because real is the same as fake. Okay. And that you can actually say here. So what I'm saying is, if the optimal strategy of generator is to say that the probability for a given x is the same as probability of data for that x, then you can come back and here and say, hey, if it's the same, then it's PD of x divided by 2 times PD of x, which is just 1/2. So at equilibrium, the generator's distribution should be the same as the data distribution, and discriminator cannot discriminate between real and fake, or between the generator and the data. Okay. Of course. So, but the problem is, so why even write about objective functions when you know what the optimal strategy of each of the players is? Okay, you can ask that, and the answer is, of course, because we don't know what PD is. Okay, we only have samples. Okay, we only have samples, and so we cannot just we don't know for every x what PD of x is, and so that's the missing thing. But we still want to figure out what we still want to train a generator or get a generator which can get samples. Okay, so we don't have PD. That's the whole issue here. Okay. So now let's come back to this picture. Okay, that I guess that's a little bit of thinking about what is the objective function and what is the optimal strategy. Let's come back to this picture. So you can see that how do we train the parameters of discriminator? How do we train the parameters of generator? Right. So that's what we need to do. So what we do is create a mini batch of real data for the current parameters of the generator. Create a mini batch of generated data. Okay. This real data and this generated data, let's say 10 images each, they don't have anything to do with each other. The first image of discriminator or whatever this mini batch has nothing to do with the first image related to the generator. Okay. Unlike VAE there was a reconstruction of the same image going on. Okay. So we have two mini batches. So what we do is create the score as in the loss of the discriminator given this data. Okay, that we can do because we have those two terms. Instead of the expectation, just take a with respect to this mini batches. Okay, get the loss, backdrop to update the parameters of the discriminator. Okay, so from the first 4 bullet points, we fix the generator, we got the loss of the discriminator, and then we change the parameters of the discriminator. Then we freeze the discriminator. Done. What we do is now again get the loss with respect to the generator. Okay, get the loss with respect to the generator. Discriminator is fixed, and now we can update the parameters of the generator, which is theta g. So this is how you update the parameters. So basically, in one case, generators first of all doesn't even matter because you have 2 samples. It's just a binary classification problem. You figure out update the parameters of the discriminator. In the second case, discriminator parameters are fixed, so it's as if you're going from you just want to change the generator parameters such that samples input of the discriminator are as close to high values as possible. D of x is close to 1 for them. That's all. Okay. Any questions here? Yeah, that's what I was saying. So to score the generator, you ignore the discriminator. So you kind of freeze the discriminator weights. So it's not anything moving object anymore. So how do you score the generator? You already produce some sample, right? So you produce some images, you pass it through the discriminator, and you got a score. So you got a dx of so you got a score for those generated images, right? So that's the that will give you the loss with respect to the generator. Remember, loss with respect to the generator is this. Loss with respect to the generator is log of 1 minus d of x. Okay, so this x is actually g of z. So g's parameters are still here. So if you think of just focus on the second term, g's parameter is still here. So you can find the gradient with respect to the g's parameters here. Actually, let me show it, the full procedure. So the minimax objective function, where we are trying to, whatever parameters we are trying to maximize, the other ones we are trying to minimize the objective. Okay? So for example, if you are trying to maximize the generator's objective, sorry, the discriminator's objective, which is this just exactly the opposite of what we saw 2 slides ago, where there's the 2 minus signs, we dropped it. So now we are trying to maximize the JD. So it's basically negative JD. So you can see that discriminator's parameters influence both terms here, and then generator's parameters influence this term here. Okay, so you can compute the loss with respect to the generator by for the given parameters, you can compute this thing with respect to the generated with respect to the, like if you produce 10 images, you will get basically 10 such loss values. So you will have for the given parameters, you'll have those images. Those images, when passed through, will produce a number. Okay, so those parameters produced a loss number, and so now you kind of minimize the loss with respect to those parameters. Okay, so on theta d, which is the parameters of the generator, you kind of do gradient ascent, and on the generator parameters, you do gradient descent, okay, because one is a max and one is a min. Now it's not okay. So this is an approximation, by the way. So you can't generally solve minimax problems this way. Okay, so minimax problems are very hard problems to solve. Otherwise, anybody can solve the solution of any adversarial game or two-player game. That's not the case. So this is just a heuristic for fixing one player's weights and minimizing the other, optimizing for other players' parameters, and fixing that player's parameters, optimizing the second player's parameters. It's just an alternating approach, but it's just a heuristic. Okay? It's not expected to converge to the equilibrium. Okay, if at all, first of all, it's unclear if equilibrium exists in general games, or so in this game we just saw it does exist. But yeah, so this is just a heuristic. Okay, but yeah, these are the two objectives that need to be solved. Any questions here, or is the generator optimization clear? So here the discriminator parameters are fixed. Okay, so it's just g theta of z is what you optimize. Okay, so as I said, the training procedure is you produce real and fake images at the beginning. Discriminator is going to try to say, hey, this is real, and this, all over the place, this kind of blurry images are fake. Generator is frozen. And how do you train the discriminator? It's just a regular backdrop. And while doing the train the generator, you kind of freeze the discriminator weights and just do a backdrop to update the weights of the generator. And so the generator architecture, again, very similar to VAE, is going to be a decon layer, so bunch of decon layers, or whatever, transpose con layers, and that's the basis for a network called DC GAN. Okay, DC GAN exactly uses this architecture, and that's why it's called DC GAN, but basically goes from a random noise or a Gaussian distribution to an image. Okay, and so once you train your GAN system, then the only component that's useful to us is basically this. Okay, going from generating some random noise, passing through the DC GAN, or passing through the decon layers, and then you get an image. So here's a example of images. So in particular for the DC GAN model, so which is exactly the architecture that you saw in the previous slide. So in particular, in this case, I think the data set is I forget the name of the data set, precise name. I think it's probably bedrooms, or I think indoor spaces or something like that. So what we're trying to see here is we already have this trained generator. Now what we're trying to do is, instead of sampling images, okay, which is what we want to do, primary purpose, what we're trying to do is, hey, what if I pick a particular z, let's say z is equal to 1 1 1 1 1, and pass it through the generator, I get some image. Okay, let's say that's the top left image, or any one of these images. Then what I'm going to do is, okay, I'll pick two images, and then I want to go from one image. So I'll pick 2 points on the latent space, on the input space, and I want to go from one point to the other. So like you start from, let's say I have all zeros vector to all ones vector or something. So you going from all zeros vector to all ones vector, you have to go through a bunch of points, right? So as you go through a bunch of points, you are producing a image for each of these z's. Okay, and that's what's being shown here. So I think the 6th and the 10th row, let's say, if you look at the 10th row, which is the last row here, it's like a you're basically transitioning from one image, realistic looking image, to another image, another realistic looking image, and you also get a sense of how the transition is happening. Maybe the windows are getting changed, maybe the bed is being changed from a certain type of bed to another type of bed, or doors are changing, and so on. Okay, so this is getting a sense of like how does did the model learn anything interesting. It's very similar to how we were doing the same thing for MNIST, by the way. So Z1 and Z2 axis, we were looking at how 7 changes to 1 or 7 changes to 9, if you remember early on with VAE. It's very similar idea. And actually, you can do something more, which is, I think we saw this type of post hoc, things that people did with word2vec. So here on the left hand side is actually you can think of left hand side as the you have the you have the vectors corresponding to the images. So although I'm showing images here, you think of the z's corresponding to the z's corresponding to these images. Okay, somehow let's say you somehow got access to these z's. Okay, then you can actually do arithmetic with the z's. Basically, add and subtract, subtract like the z1 minus z2 plus z3, where these three z's typically corresponded to these three images. Okay, generated images. Then you can get basically something like, hey, subtract information related to man and add information related to woman, then maybe you can get these types of generated images. It's just a byproduct, things to kind of understand whether your model is maybe working or not. This is just partial views, but kind of gives you an idea. Any questions about this? Yeah.
So you mentioned that we go from one vector to another vector.
That was the previous, yeah. This,
one point to another point.
yeah.
So like, what is that another point? We know there's one point there's the z vector that we have.
No, there are two specific z values, z vector values. When I say one point to another point, there are two z vectors, like 10, let's say 10-dimensional vector, 10-dimensional vector. It turns out that, basically in this, by the way, these are like 10 images, 10 cross 10 type of thing. The left hand image corresponds to one z vector, and this right hand image corresponds to another z vector, and they're just interpolating to see. You can draw a line, or basically a vector between them, and just pick intermediate points, like make it a grid, and then evaluate what would be the generated image for each intermediate version of like a convex combination of them, and those are these images. No, this is after training. This is all whatever we're doing now. So in this again, this is all after training. We discard all the discriminator stuff. This is just focusing on the generator, trying to kind of understand what it's doing. This is after training. Okay, this is not related to training process. No, at the end we have a generator like this. This is a generator. This whole thing is a generator. If I give a random z, I'll get a random image. Okay, they just figured out what is the z to give to get to the leftmost image, what is the z to give to get the rightmost image, and then they're saying, hey, how do I go from, like, what happens when I give an image, what happens when I give a z which is a like in between these two z's, like some convex combination of them. Okay, so it's just an exploration of the, once your trained model, it's like very similar to CNN debugging. It's just an exploration of what is it doing. It's doing interpolation. It's very similar to what it did for VAEs, right? With MNIST data, we had like a z1 z2, where changing z1 and z2, we're changing from 7s to 1s to 9s and so on, right? Same thing with this. We have a trained model, trained generator, and we're just changing, hey, there was a z corresponding to this guy, there's a z corresponding to this guy, this image, sorry, and the Z corresponding to this image, and so we're just trying to see if their combination like this kind of gets us the glasses on the woman type of an image. Okay, and it seems to work for this particular example here. Okay, so there is an issue with GANs, which is actually what makes it hard to train. Okay, so all the style GAN 2 or even vanilla GANs, they are hard to train in general, and that's related to this idea called mode collapse. Okay, so what is mode collapse? It's the idea that because the information is not, there is no direct loss function, right? So there is some training data. Training data is just like some samples from the original distribution, which somehow is captured in the discriminator, and which somehow influences the generator weights, so that generator can now generate data which looks like the training data, right? Which looks like the original data. So the mode collapse idea or issue which people observe, and this is nothing to do with images, by the way. This is just even if your data set is just numeric data set like vectors, like in particular, for example, here the data set is actually a two-dimensional data set. Okay, where each data point is just a tuple, two-dimensional vector, x comma y. Okay, x1 comma x2 numbers. Okay, so let's say the original data has a distribution like this. Now you can say, hey, what does this distribution look like? It's actually a bunch of, like, it's a top view where there's a bunch of Gaussian distributions which are equally distant from each other in a circular pattern here. Okay, so it's like most of my data points come from this hump or this hump or this peak or this peak and so on. Okay, now, so this is a very particular choice that the authors made to show this particular phenomena, which can happen even with this two-dimensional data set. Then certainly it can happen with higher dimensional data. So what's happening is, with this type of data, GAN, for example, needs to learn this distribution, right? Eventually, if you remember, the equilibrium situation is that it exactly figures out this distribution. But you can see that as you do lots of training, like step 5K, 10K, 15K, 20K, or just think of it as proxies for like a lot of training. Okay, so you can see that mode collapse is basically that it's only picking up one of the modes. Okay, so it's first time it's saying, hey, after some time it's saying, hey, the most of the distribution is here, and then suddenly it's jumping to a location here, and some other location, some other location, some other location. So basically it's just, although it's not very clear here, but it's basically jumping between these peaks here. Basically, it's not exactly looking like that, but it's basically jumping between these peaks in the sense that it's not able to capture all the peaks simultaneously. Okay, but I mean, this one, then the in particular, some authors you can see in this tutorial, they try to fix it such that you can try to get to all the peaks. You can get a distribution which is distributed over all the peaks if there are multiple peaks. Okay, mode collapse means that instead of having these 8 modes, there's only one mode after a lot of training, and that's a collapse of all the other modes while doing the GAN training. Whereas some fixes kind of led to capturing most of the modes here, all the modes here. Okay, that's just a minor point, not super important, but I'm saying, so what this slide is trying to illustrate is that GAN training, if you're gonna do from scratch, has mode collapse issue, and so you may not be able to train GANs, and so they are harder, one level harder than training things like CNNs or VAEs and so on. Okay. So here are some examples to show how training improves from left side to right side. Like GANs are initially producing very blurry things. So the GAN, sorry, in particular DC GAN, for example, it's producing blurry stuff, and then eventually it kind of learns to produce realistic looking images. Okay, realistic for to full generator, but if you zoom in and see, they are, of course, the images are not really natural images. Okay, you can see the artifacts clearly. Okay, I guess it's getting closer to like something like deep fake stuff. Okay. So any questions about GANs? Now I'm going to spend a couple of minutes on trying to just compare and contrast VAs and GANs. Okay. Any questions before that? Okay. So just to, I mean, I'm gonna just kind of summarize what we saw in the past lecture and this lecture. VAs and GANs are just examples of two samplers. Basically, the objective as within unsupervised learning domain, we are only looking at one particular problem, which is sampling, and sampling from very difficult data modality, which is images. Okay, So these two are generative models that use either some sort of log likelihood or some sort of this like adversarial objective function to get to their sampling procedure. So let's focus on VAEs. VAEs are generative models. Okay? So they are actually explicitly talk about joint distribution, and then they try to optimize regularized log likelihood. Okay, that's what we did. They tend to achieve higher likelihoods of data, higher than, for example, GANs. But first of all, there's no likelihood for GANs, but they tend to achieve high likelihoods for data. But the generative samples don't have like a sharpness of real world images. Okay. But the thing is, you can compare generated images with the original images because there's an encoder as well. So in the VAE, there's an encoder and a decoder, right? And so they are members of what is called graphical models family, and so they have their principled theory of defining joint distributions, defining approximations to likelihood, defining all sorts of things that we know with this as a probabilistic models. Okay. Whereas GANs are models which use a like a game theoretic loss function to approximate to learn basically. So the discriminator uses supervised learning, and so the generator learns via the discriminator. Okay. So there's no constraint that a bed should look like a bed. So there's no constraint at each image level. Okay. So there's no image level reconstruction error or anything. To try to solve an intractable game, this minimax game, intractable because we don't know PD, and if you know the PD, then we know what the equilibrium is, but we don't know the data distribution. Okay, tend to more difficult to train than a typical neural network. Tend to have sharper images for empirically observed property, and so you start with latent random variable like Z. You flip, you create a basically you start from random noise, and then you apply G, then you get an image. Okay. In VAEs, you start with a G. We start with a Z, which is like from a random Gaussian. You pass to the decoder, and then you can potentially also do one more sampling, which is that you pass to the decoder, it'll give you the mean and the covariance or variance vector, and then you again sample to get the image. Okay. There is no further, there's no Markov chain like sampling needed, and they have some better properties. Okay, but this was actually old. So 150 GAN models from 2000, I guess 16 to 19. Now it's 22. 3 more years. I think maybe more than 1,000 GAN architectures have been proposed probably. But there are a lot of interesting research, especially because it's a interesting model in the image or vision area. Okay, so there are a lot of papers, a lot of models here. So to summarize, on the top you see VAE type of architecture where you always try to focus on reconstruction while training the decoder. Okay, and you impose a constraint that the marginal probability of Z is Gaussian. Okay, with those two you're training parameters here using that evidence lower bound maximization idea. Okay. So given an image, you can actually easily find the Z, because clearly if you give me the image, I can use the encoder to tell you what the Z is. Okay. So you have a probability distribution as well over X, but it generally produces blurry images. With GANs, the idea is you start with the randomness, which is Z, and then pass to the generator, and that's it. It produces an image. Okay. Ideally, the image that it produces is realistic enough so that the discriminator is pooled. Okay, that's how you want to train up to that level. But given an image, it's kind of hard to figure out what the Z is, because if you tell me this is the image, what is the Z that produces it? It's hard. Okay, and that's why I mentioned the vector arithmetic. How did they find it? So those 3 images. That was probably hard. They tried out a bunch of images and bunch of Z's which led to those images, and then tried to do vector arithmetic on that. But there is no distribution on X. Okay, there's no distribution on X here. I mean, no explicit distribution on X, because start with Z, you have a derived distribution on X already, but there's no explicit distribution on X directly. That's considered here, okay, because the loss function and all that is different. Okay, so both are new models from the last 10 years or so, 8 years or so. They're useful in applications mostly related to image processing, image denoising, like removing noise from grainy images or low resolution images. It's called super resolution. Okay, so information to increase the resolution is there in these networks. Okay, so you can have a blurry low res image, for example, security image or something like that, or old ancient image, and they can be colorized or increased in resolution. These models can also be used in reinforcement learning. We'll see reinforcement learning later. Generally, mostly for generation, okay, image generation, artistic artifacts, and so on. Any questions about GANs and VAEs? Yes, I mentioned, right. So the models themselves, model descriptions themselves, are not specific to images. Like when I was talking about VAEs, I mentioned they can be used for graphs. Graphs kind of look like images because you have an adjacency matrix, and so it's like a image, if you think about it that way. You can extend GANs to text as well, but I'm not very aware of that direction. Okay? So you can, I'm sure there are attempts that you can find, but for text it's unclear. Like GANs will generate some text, and you have to say, hey, is it a realistic looking text, like a realistic enough for a human to get fooled or not? You can do it this way as well, but I haven't seen empirical success, so I'm not aware of it. Yeah.
I read an article where people were trying to create music.
Yeah.
It's actually somewhat related to
Yeah. Yeah. So creation of music, yeah, generators will generate new music, I guess, whatever the base units are there. Yeah, you can do that. So you want to generate, you want to learn musical patterns, but you don't want to. So you can use both VAs and generate or GANs to kind of learn new musical or generate new musical patterns. Yeah, you're thinking of distribution or musical patterns, and you have some training data of musical patterns, and then based on that you are trying to learn a model which can generate new musical patterns which are not there in the training data. Yeah.
That will what is the GAN what is the discriminator doing GAN?
Discriminate between the two musical patterns.
Whether it's real or not.
Yeah, same thing. Discriminator is always trying to produce it's a binary classifier. So musical pattern, however you encode it, for example, as a spectrogram or as a, it doesn't matter. It's unclear. Like it depends on the how you encode it.
You have to select a metric basically.
Yeah.
See how it's real.
No, I mean, so you will have to have a representation of a musical pattern. So when I say representation, just think of this as, so musical patterns can just represent it as sentences if you want. I mean, it's literally a sequence of tokens if you want. Then one sequence of tokens it's real, the other sequence of tokens it's false. Generator's objective is to create realistic looking sequences of tokens. Yeah, like if you think of MIDI files or something. Yeah. Okay. We have 20 minutes, so let's pick up the next chapter. So what I'm going to do is, since we have 15-20 minutes, it's going to be very lightweight. It's just going to motivate like decision making and towards how decisions are not an afterthought generally. So far we have seen mostly classifiers and whatever, even unsupervised learning models, but there the decisions are simple. Okay, where like if classifier says, hey, it's going to rain tomorrow, I mean, you can just say, hey, because it's going to rain tomorrow, I'm going to bring an umbrella, for example. But sometimes the decisions are complicated, where the classifier classifies, for example, hey, this person has a lone default probability of 0.1, this person has a lone default probability of 0.2, this person has a lone default probability of 0.5. And given that I only have $1 million to as lender to give, given these lone default probabilities, I may have to like take a more intelligent decision of how to split my, give loans, for example. Okay, so there it's not clear. Just because loan default probability is something doesn't mean it's not a binary decision, because you may have a budget constraint or a resource constraint, for example. So decisions can be complicated, but we'll look at that, and we'll also talk about like a particular paradigm called reinforcement learning. So let me get started with the with some motivation actually. So it's just trying to switch gears and trying to bring decisions into the picture. So we have seen quite a few different types of model architectures, but there's a disconnect between just supervised learning or anything like that to decisions. Okay, and in fact, this also is not, doesn't give whatever we do in the next today's next few lectures also is not a full picture of how learning can be tied with decision making, because the type of learning we've seen is mostly association based learning. We're not really making causal claims. Okay, so we're not talking about inputs really leading to the output in a causal way. We're just saying that inputs are correlated to output. Okay, mostly. So, but that's one angle, that we are not looking at causality. But the second angle is that, which is what I mentioned earlier, is that even if you build a forecasting model, that model may be not enough to make intelligent decisions. Okay, so you may have to do something more, like decisions can be complex, or decisions may need to be taken again and again with some new learning and so on. Okay, so we'll talk about that. So so we're going to look at one particular subcategory of this decision making business. Okay, I guess data driven decision making thread. Okay, which is called online machine learning. Okay, which we're not going to look at this lecture, next lecture. It's called online machine learning, where what you do is you're basically in a for loop where you get some data, make some predictions, get some new data, make some predictions, get some new data, make some predictions. Okay, so it's like incrementally improving your model. And you may say, hey, what is the big deal? You keep getting new data, so you can always improve your model. But the idea is the decisions you make influence what data you have for the next round of improvement. Okay, so we'll briefly discuss that today. But later on, we'll talk about reinforcement learning, which is again one particular way of making data-driven decisions, and so it has to have some. It makes sense in some conditions, and we'll talk about which conditions this particular technology makes sense. And it has been used, and I think you saw a Tesla video earlier. I think I showed you where self-driving going from point A to point B, and some other applications. So RL is the type of technology behind that. And then towards the end, we're going to mix deep learning stuff that we saw, so far, and the decision-making business, and merge them together to look at one particular approach called deep reinforcement learning. Okay, so let me look at some examples. First, complex decisions. Okay, this is nothing to do with machine learning yet, in the sense that machine learning would be like inputs to this decision-making process. Like typically, for example, inventory management, resource allocation, routing problems. These are all problems which involve multiple predictions simultaneously, or multiple different types of predictions, and then making a decision of how much to order for your inventory in your warehouses, or who to provide customer service first, for example, if you have a high volume of calls and things like that. Okay, these decisions are not simple transformations of predictions. Okay, that's what I want to say. And so that's one angle. So there may not be a simple transformation from your forecast to a decision. The second thing is a technology that we look at, which is called, I guess, reinforcement learning, which kind of relies on data-driven decision making and continual improvement. Okay, and this is where I said you build a model, make some decisions, get some feedback data of how you did. Based on that, you again build a model which makes hopefully better decisions, get some feedback data on how you did, and based on that, you kind of improve again your decision making ability, and so on. Okay, so that's the reinforcement process, and that's one direction that we look at. In fact, back in 2012, a bunch of researchers from DeepMind kind of showed how to use this reinforcement idea of trying out something, learning from how you did, to improve what you would try out next, using a model and see how it did, to improve yourself next again and again, on what is called the Atari learning environment. It's just the Atari games from 1980s. Okay, so these are just 2D games, and so they were able to build a deep learning model which can play these games. Okay, after some time, after some training. This is the learning process where the model trains and learns to use the joystick in some ways, and then it learns that it may not be good such good ways, and then it'll improve on that. Okay. Here's another example where again reinforcement learning kind of, this is from 2016, and since then there are other models that have come up, but basically on the left you're seeing a cover page of a scientific journal called Nature, and which is with the photograph of what is called game of Go. It's a board game like chess. Okay, and on the right side you're seeing a photo of two players. I mean, in fact, the left side is actually a representative for the AI player called AlphaGo, and the right side is the human player at that time, top ranked player in this game, and they're playing and they played 5 games, out of which 4 games were won by the AI system. Okay, and that system AlphaGo was based on some reinforcement learning ideas. Okay, this idea of taking some decisions, learning from feedback, taking improved decisions, learning from feedback, and so on. So the outline is really for this lecture is about understanding this idea of taking some feedback and improving yourself. And then there is a small particular trajectory that we're going to go through, which is one is A/B testing that I'm going to mention when we get there, which is about using statistics and doing randomized control trial to figure out which decision is better. And then the subsequent ideas are related to how to do the same thing, not exactly randomized control trial, but to figure out which decision to make, which decision is better in a little bit more sample efficient way, in the sense that you don't need to kind of do a lot of trials in the randomized control trial to figure out which option is better, which decision is better. That's multi-arm bandits and some variation related to that. And this is what is going to lead to the reinforcement learning setting. Okay. So let me mention, so I'm going to repeat this early next class, but I want to mention at least a template, because I've been saying this pattern. In fact, what I said earlier when I kept saying decisions, improve yourself, decisions, and so on. What online machine learning or even reinforcement learning is about is that you optionally observe something. Okay, what is the current situation? Current situation just means like, hey, this is my state of inventory, or this is my board, positions. Let's say in the game of Go. Then you make some action, take some action. Okay, maybe you restock inventory at some locations, don't restock at some other locations. Okay, and then you get some feedback. Maybe you lost some sales at some location. You made a lot of revenue in some other locations. Whatever it is. Okay. Obtain feedback on the chosen action. You only get feedback on the chosen action. You don't know what would have happened if you had done something else, by the way. And then you keep this on a repeat. So every month you have to take inventory decisions. You take some inventory decisions. You get some lost sales potentially, or improved revenues, or whatever leftover merchandise. You take another inventory decision next month, another inventory decision next month. Let's say retailer, right? So this for loop where you're taking an action, getting feedback on an action, and then hopefully that from that feedback you're learning that action is probably good or not, and then hopefully improving yourself. Okay, so this choosing an action is exactly a prediction type of problem. Okay, choosing an action could be just a forecasting type of problem, but then you're getting data for exactly what you predicted and not what else could have like if you did some other action, what would have happened. Okay, that's a big feature of this type of setting. Okay, whereas contrasted with supervised learning, let's say I'm doing classification. If you give me an image and I say, hey, there's a dog, I say glass is dog. Okay, the feedback, you can give me 2 types of feedback. You can say, hey, it's not a dog. Okay, but that's the type of feedback I'm talking about here, which is the feedback on a chosen action. But you can also give a feedback which is saying, hey, it's not a dog, it's actually a cat. Okay, that's more information. When I say it's not a dog, but it's a cat, then you not only know what would have happened if you had said dog, you also know if you had said cat, you would have actually gotten the prediction correct. Okay, so that's the feature of supervised learning which is missing here. Okay, but even though that feature is missing, which is that I don't have feedback on things that I did not do, I will still learn over time, which is I'll try out something, try some decisions, get feedback on the decisions, improve myself, improve my prediction model or whatever it is, and take better decisions over time. Okay, so that's the gist. And basically the goal is to optimize. I want to get better and better feedback. Okay, so that's the only way I can figure out whether I'm doing well or not. I'll come back to this assumption, but let's look at an example, right? So in this example, I'm not gonna, this is the last slide, I'm not gonna go to the next slide. But so what in this example, the action that the company, in this case the website owner, needs to make is which articles to show. Okay, let's say they have a collection of 50 articles, and from which there's this limited real estate on the screen, and so they need to show some 10 articles, okay, to an arriving user, right? So maybe the arriving user, maybe the demographic which visits this web property, they're all like sports, let's say. Initially, maybe the web owner doesn't know them, so they try something. They try some actions. Okay, they maybe show sports and music and current events or something like that. Okay, and then they get a feedback. The feedback is going to be engagement with the website, right? So based on the feedback and the actions they took, they should go back and say, hey, maybe I should show something else. Maybe I showed a lot of current events and there was little engagement. Maybe I should show something else. And then eventually they'll figure out, hey, I should keep showing sports, because most of my demographics who visit my page are sports people. So that's the type of online learning. Okay, there's a loop where you try something, you decide something. Okay, and this decision of what articles to show can be a prediction model, right? It could be, it could be, for example, if there is a user context of user information, IP address, or time of day and things like that. Given that, you can come up with a list of articles to show. That could be prediction model. But you want to improve it because now you're learning. Depending on articles you showed, something happened. User engagement happened. Based on user engagement, you decide, hey, that's not the right things to show. I should probably show something else. That feedback has been incorporated to update your models. Okay. In fact, these folks at Microsoft did this, and at least on this website, and 5 years ago. And they showed some quantitative they showed some tangible improvements in click-through rates and things like that, as an example of this idea that you have to improve over time. You have to keep making decisions, keep getting feedback, and you need to improve over time. It's very different from the batch process that we've been seeing. Batch, in fact, one-time process that we are seeing, where we have collected batch data, we build a model once, and that's it, and we are kind of not thinking, at least, about what else to do after that process, right? Okay, so let's pause here, and we'll come back to this online machine learning, A/B testing, and bandit stuff next time.